Hey guys, this is Mrs. Harvin, Algebra 2, and this is section 2.5, Special Functions. This is attempt number 2 in this video, so hopefully this one works. Our biblical integration for all of Unit 2 is this: relationships exist everywhere. God desires us to encourage each other and have a relationship with other Christians in order that we may all share in the glory of Christ. Now, this chapter we're talking about relationships in math between the x and the y function. And we also see relationships in science between animals, like symbiotic relationships, and we also have relationships with each other. Everything that God has created works in tandem with all other parts of his creation. So we need to make sure we understand how these relationships work. Our lesson objective is this: you, the student, will identify, evaluate, and graph constant, piecewise, greatest integer, and absolute value functions. A constant function is when your y variable, or f of x, equals a constant number. So remember, f of x is just another name for y. And it's a horizontal line with a y-intercept of 0 and whatever that number is. So if you have f of x equals 3, then on your Cartesian plane here, you're going to have a horizontal line at y equals 3. Because no matter what your x value is, your y equals 3. So when x is 1, y is 3. When x is 2, y is 3. When x is negative 1, y is 3. So a constant function is when your f of x equals a constant number. A vertical line represents multiple values of the range for a single domain value, and it is not a function. So in this case, we have x equals 3. And you can see we have a vertical line, and x equals 3. When x equals 3, y is 1, and y is 2, and y is 3, and y is negative 2. So you have all these multiple values for only one domain value. That is not a function. It does not pass the vertical line test. A function whose value is defined by different expressions for various intervals of its domain is a piecewise function. Basically, it's a function with different pieces. So you can see we have piece 1, piece 2, and piece 3. And each of these pieces is going to have its own domain and its own expression or equation for the line. Okay, this is how we would write an equation or a function notation for a piecewise function. Okay, we're going to start with this first piece right here, and we're going to set our domain. And if we look at our domain, we know it stops here with an open circle, and this arrow tells us that it goes on to infinity. So our domain is that x must be less than negative 2. Any number less than negative 2 will work for this piece. And then we're going to write the equation for the line. In this case, it's x plus 3. Our slope is 1, and if we extended this line, it would intercept the y-axis at 3. For our second piece, you can see our domain is between negative 2 and 2. So we write that x is between negative 2 and 2 using correct notation there. And then we write the equation for this line. And the equation for this line is x squared. This is what we call a parent function. This x squared function always looks like this U shape. It's one that we just have to memorize. And then our third piece, our domain is from 2 to 5. So we write this domain that x is greater than 2 but less than or equal to 5. And then we write the equation for the line. Well, this is a horizontal line. This is a constant function. So our y just equals 1. So those are our three pieces. F of x equals x plus 3 for this domain. It equals x squared for this domain. And it equals 1 for this domain. So we put all those pieces together. The domain of a piecewise function is the union of all the domains of each piece. It's all the x values combined. The range of a piecewise function is the union of the ranges of each piece, all the y values combined. So if we're looking at the domain of this piecewise function, we see from here to here, there's a continuous line. There's not an x value that doesn't have a blue line. So our domain is going to go from here to here. Our range is going to be from our lowest point to our highest point. Again, for each of these y values, we can see that there is a line. There are no holes. Our domain for this particular function is that x must be greater than or equal to -4 and less than or equal to 3. And our range is that y is greater than or equal to 2 and less than or equal to 6. Now, when we take a look at this domain and range, you can see we have some holes. When we're looking at the domain from here to here, everything's covered. But then from -1 to 2, there's this gap. There's nothing there. So we can't include that in our domain. In our range, you'll see something similar. We have a line here, but from here to here, there's nothing. There are no lines, so that is not included in our range. So how we would write the domain is this. We have first, our first piece, the domain is -6 to -1. And then our second piece is x is greater than or equal to 2 or less than 4. We cannot include any of these numbers here in the domain because there's nothing there. When looking at our range really has just two values. Our range is either 2 or it's 4. Our y value is either 2 or 4. All right, see if you can state the domain and range of this one on your own. Pause the video and come back and check it when you think you've got the answer. Our domain for this function is x must be greater than -4, greater than or equal to -4, and less than 5. So when we look at our domain, there is a break right here between our pieces, but no x values are left out. So we have something here at 1, there's a coordinate. At 1.1, there's something. At 1.2, there's something. At 1.3, there's a y value. So our domain does not have a break in it. Our range, however, well, what do you think? Does our range have a break? It does not. Again, there's this little break right here for these y values, but if you look, we've got it covered. At this y value, there is a corresponding x value. So our range is covered, and our range then is -3 all the way up to 6. Write a piecewise function rule describing the graph. Find the domain and then the range. So when we write a function rule, we want to look at each part at one time. So we're going to look at this piece, tell the domain and the equation. The second piece will identify the domain and the equation, and then the third piece. For our first piece, our domain is that x must be greater than -4, but less than -2. And the equation for our line, remember this is y equals mx plus b, y equals 1x plus 4. Our slope is 1, and our y-intercept, if we were to continue this line, would be 4. Let's go on to our second piece. Our domain for the second piece is from -2 to 0. And the equation of our line, it's a horizontal line. We know that's a constant function. So y equals 3, or f of x equals 3. And for our final piece, our domain for this piece is that x is between 0 and 2. So x is greater than 0. Actually, that should say greater than or equal to 0. And less than or equal to 2. And our equation for this line is -3/2 x plus 3. Our y-intercept is 3, and our slope is -3/2. The second kind of special function we're going to look at is the greatest integer function. It returns or gives us the greatest integer less than or equal to x. The domain would be the set of all real numbers, and the range is the set of integers. Our notation is this: f of x equals square brackets x. Square brackets tell us we need to find the greatest integer that's less than or equal to whatever's inside that box. So if we look at x, the greatest integer that's less than or equal to 1.5 is 1. The greatest integer less than or equal to 2.7 is 2. 3.4 is 3. 1. The greatest integer that's less than or equal to is 1. When we go negative, don't forget the closest integer to -0.75 is not 0, because 0 is greater than. We want one that's equal to or less than, so 1.4. And the greatest integer closest to -3.4 without going over is 0.4. When you graph this function, you'll notice that it kind of looks like stair steps. So let's see, 1.5 and 1 would be right here. 2.7 and 2 would be right about here. 3.4 and 3 would be here, and 1 would be here. So you can see that each of these falls on those little pieces of the function. All right, let's evaluate f of x equals, and then the greatest integer, x. For f of 2, we want the closest integer to 2. Closest integer to 2 without going over is 2. For f of 3 halves, the closest integer to 3 halves without going over is 1. So 3 halves would be right here, but the greatest integer would be here. The f of negative 2/3, well, the closest to 2/3 without going over that would be negative 1. So on the number line, it looks like here, but the greatest integer function would place it here. So how we graph these on a number line and in our greatest integer function are going to look a little bit different. The absolute value function is the third kind of function that you need to know, and it is also a piecewise function. The absolute value function is another parent function that we need to know. If you remember, I said x squared. All functions with x squared are going to have that u shape, and now all functions with an absolute value are going to have a v shape. Our domain for absolute value functions is the set of real numbers, and our range is anything non-negative. We know that absolute values cannot be negative on the graph. It's going to look like this as a piecewise function. For the absolute value of x, it's going to be x if x is greater than 0, and negative x if x is less than 0. All right, let's take a look at that. So when x is greater than 0, we plug these into our absolute value equation, and we get 0, 1, and 2. When x is less than 0, negative, so negative 1, negative 2, it gives us still a positive 1 and 2. So today we identified, evaluated, and graphed constant, piecewise, greatest integer, and absolute value functions. If you have any questions, be sure to ask me next class. Have a great evening.